Okay, write a two-column proof for 10. Looking at the diagram, got a couple different triangles here. The triangles in question are triangle ABE. I'm going to use a different color here. Triangle ABE and triangle DCE. Let me use a different color. DCE. Alright, this proof is going to be kind of lengthy. Let's go ahead and put our two columns here. Statement and reason. And what we have is that angle EBC is congruent to angle EBC, ECB, sorry. That's given. Not part of the triangles that we need. However, they both form a linear pair with two of the triangles that we need. So we might have to use that. We have that line segment BE bisects is an angle bisector to angle AEC. It's given. Okay, so we have BE. Okay, AEC, so 1 and 2 are congruent. And we have that CE bisects angle DEB, which is given. And we're trying to prove that triangle ABE is congruent to triangle DCE. Okay, now again, right now we have one side. I forgot to write that down. Sorry. It's line segment EB is congruent to line segment EC. Also given. So right now we have a side. So that's all we have. But what we do know is that BE bisects angle AEC. So we know that angle 1 is congruent to angle 2. Look up here. Okay. Line segment BE bisects angle AEC, cutting into two equal pieces. And we also know that line segment EC or CE bisects angle DEB. So we know that angle 2 is congruent to angle 3. And that's the definition of angle bisector. Now if 1 is congruent to 2 and 2 is congruent to 3, then we know that angle 1 is congruent to angle 3. And you can use substitution or transitive property here. It's actually the transitive property. We'll use substitution property if that's what you prefer, that's fine. So we know now that this angle is congruent to this angle on the side and the side. The last thing we need is angles 4 and 5. What we can say about angles 4 and 5, what I want to do is I want to put a 6 and a 7 here. 6 represents angle EBC, which we have up here. And angle 7 represents angle ECB, which we have up here. They're congruent to each other. And what we can say is that the measure of angle 4 plus the measure of angle 6 is equal to 180 degrees. And that the measure of angle 5 plus the measure of angle 7 equals 180 degrees because they are both linear pairs. Okay, I'm going to take this and I'm going to slide this down and get the whole thing. Okay, now if they're both equal to 180, we can set them equal to each other. So the measure of angle 4 plus the measure of angle 6 equals the measure of angle 5 plus the measure of angle 7. Substitution again, I guess kind of in a way the transitive property. We want 4 congruent to 5. That's what we're trying to prove so we can get this final angle. So we need to get rid of this 6 and 7. Well, by substitution, remember, angle 6 here, and I guess this is kind of a fudge. I guess this isn't exactly correct. 4 is angle EBC. So here, we could simply say that angle 4 is congruent to angle 5. That's what this is saying right here. And I guess we could kind of say substitution. I don't know if that's really necessary. But just for the shorthand's sake, we're using those numbers down here. We could say that 4 and 5, 6 and 7. 6 is congruent to 7. What we can do down here is we can say the measure of angle 4 plus the measure of angle 7 equals the measure of angle 5 plus the measure of angle 7. Substitution, and then if we subtract 7 from both sides, we get that the measure of angle 4 equals the measure of angle 5. That's a subtraction property of equality. And what that allows us to do is to say that this angle is congruent to this one and use angle, side, angle to prove these triangles congruent. I know that was kind of messy, a little bit of mess right there. But that is one way that you could definitely do this. And it's a pretty difficult proof. Take a look at it, see how much of that can sink in, and we'll talk about it more.